It's finally time for the factory pattern. If you're not already familiar with this playlist, what we're doing is that we're walking through all of the patterns in this book, Head First, Design Patterns, one by one. So if you're not already subscribed, now's a good time to subscribe so that you won't miss the next pattern. And by the way, this book, Head First Design Patterns, is a great book if you're new to design patterns because it's very pedagogical, it has all these images and all of the narrative and all of that stuff. If you're really just looking for a reference book, this is not the book, but if you're new to patterns, be sure to get this book, link in the description. But now, factory pattern. So, the Head First book talks about 3 versions of the factory pattern. 1, the simple factory. 2, factory method. And 3, abstract factory. Now, in the book, they're saying that simple factory isn't actually a design pattern. And I completely agree with this. And for that reason, we're not actually going to talk about it because it's not a pattern. And, well, by proxy, we'll probably talk about it when we're talking about the factory method pattern, because it's sort of an increase in abstraction when you go from the simple factory to the factory method. I'll try and remind us so we'll see what that was all about. But in other words, we'll talk about the factory method and the abstract factory. And in this video, I want to talk about the factory method, and in the next video, we'll talk about the abstract factory. So without further ado, let's get into the factory method. So let's first start with a little bit of a narrative. Why do we need the factory method pattern? Why do we need a concept called a factory? Why do we need such a thing as a factory? Now, think about it this way. In our code, we use a lot of different objects. We have classes in object-oriented programming. We have lots of classes and we instantiate objects from these classes. And then we use these objects in a bunch of different ways. Now, when we talked about strategy pattern, you could argue that what we were doing is that we were programming by wishful thinking. We were saying that when I'm in this particular method, let's imagine that I already had a thing that does such and such, right? Instead of saying that, let me construct a thing here where I am in the code, I would say, let's assume that I already have such a thing and that I am past that thing via some constructor or via a method. Essentially dependency injection. So the idea of the dependency injection, right, is you can think of it as programming by wishful thinking. You can think of it as that you put yourself in the situation where you say, what if I already had a thing that did this and this and this? So that's a way of abstracting away the construction of an object, away from the place that used that particular thing. But here's the thing. At some point in the program, that thing that you're passing around has to be constructed. If you think about it very concretely, the keyword new, you have to new up your class. You have to instantiate your classes at some point in the program. Inevitable. If we're doing object-oriented programming and we're not just using static methods everywhere, which by the way don't do that, then we need to instantiate objects somewhere. And the question is, where do we instantiate them? And this is what the factory pattern in general is trying to address. It's trying to say, when you are about to instantiate, let's encapsulate that instantiation so that we can make it uniform across all places, so that you can use the factory whenever you want to instantiate, and the factory is responsible for instantiating appropriately. Now, it might seem a little bit silly to create a wrapper around the keyword new, because if the difference is saying new animal or calling create animal on an animal factory class, then it seems like you're just substituting one line for the other and you start to wonder what the benefit is. But think about it from these two different perspectives. So A, it's possible that the instantiation is actually very complex. In other words, it's possible that in order to instantiate an animal, you might need computation. You need some kind of business logic in order to determine what parameters you want to pass to this particular animal and maybe which animal you actually want to construct. That's on one hand. On the second hand, so B, it's also about polymorphism. If you have a factory that wraps your construction, and if that factory is an instance, then you can swap that at runtime. You can swap that instance for an instance of another factory. Polymorphism. Let's get into this in more depth. Let's try to be a little bit more concrete. So here's what I'm saying. When we're talking about factory pattern, we're saying that in your system, you have a bunch of classes. So you have A and you have B and you have C. And let's assume that these classes all either inherit from some superclass or implements some interface. Let's call it I. So in other words, A's and B's and C's can be treated as the same type. And this is, of course, I mean dot dot dot. Like you can have any number of classes in your system that can be treated as the same type, right? That follow the same kind of contract. It doesn't matter what this is, right? It could be like you have cat and you have dog and you have duck, and then this superclass is animal. So these are a bunch of animals in your system. Whatever. Now, let's say then that at a particular point in your program, you want to instantiate one of these things. For some reason, in this position in the program, you want to be able to use either an A or a B or a C. And the point is that upon entering the place, let's say the method, upon entering the method in which this line is located, you cannot from the outside, or you cannot when entering here, trivially, know which one you want to create. If you knew which one you would create, this is not a factory method, it's not a factory problem. Then you would simply use, for example, dependency injection. You would just pass in an instance of an A or an instance of a B or an instance of a C if you knew which one you needed. But if you don't know which one you need, in other words, if you actually here want to construct that thing, and going back to what we were saying before, point one, if when you're about to construct this thing, you actually need some kind of logic. Now, what do we mean when we say logic? Let's say that I'm building a national park simulator. I'm building a simulation of like a forest or whatever. So in other words, what my program will do is that it will spawn ducks and cats and dogs, and they'll jump around and do stuff within this simulation, right? So it's like we have some kind of system that pretends to be a park wherein animals live. Super silly, but I mean, it doesn't really matter. The example doesn't matter. The point is that we want to instantiate these different things, and for some reason we need some logic that determines which of these things that we want to instantiate. And for example, the reason I'm pushing for the forest, the simulation example, is that we could say that, okay, by the way, I mean, wild dogs and cats in the forest, never mind, but just follow along. So we could imagine that, for example, what you would want to do is that you want to flip a coin, right? You want to randomize something, non-determinism. You want to randomize, and then you want to say that either I want to create this thing, or I want to create this thing, or I want to create this thing. By the way, if you haven't already noticed, if you've got the Head First Design Patterns book, I hope you forgive me for completely diverging from the example that they're using. So some of the examples in this book are excellent, in my humble subjective opinion, and some of these examples are absolutely catastrophical. And for the factory pattern chapter, I just can't for the life of me figure out how they would think that this is an easy to understand example. It might just be that it's non-relatable for me, because so what they're talking about is that they're talking about different types of pizza. So it's like New York style pizza and whatever that other LA style pizza or something like this. And maybe it's just that not being from neither New York or LA, that doesn't really make any sense to me, because I'm not intimately familiar with these pizza types. If I was, maybe that would make perfect sense. But to me, that's just completely confusing. So I'm choosing an example which is extremely different from the example here. I hope you don't mind. What we will do is that we will look at the definition and we'll look at the UML in this book. Back to the example. In other words, we were saying that we randomly want to create either an A or a B or a C. Now, you could say that, okay, well, that's silly. I mean, that's a simple piece of logic, so you would just put that logic here. If the number is such and such, create this. If the number is such and such, create that. If the number is such and such, create that. But you could imagine that this is only one of the places where we're doing this. Let's say that we had another place where we would also want to use the same kind of logic, right? Where we either create this, or we create this, or we create that. And imagine that the logic that we're describing here, like let's say random creation, is only actually one of the kinds of logic we want to use to create these things. Maybe there are actually other ways, which could be, for example, let's say that we have some kind of balanced creation where we want to use some kind of random creation, but maybe we want to maintain an equal number of these at, let's say, every third time. So in other words, like we randomly create either an A or a B or a C. And if it happens that we create an A, then we only randomize between B's and C's. And if it then turns out that we create a B, then next time we'll create only a C, and so forth and so forth. I mean, it's just a silly example, but what I'm emphasizing is that depending on your scenario, depending on what you're building, you might have different business logic that determines what thing you want to create, what thing you want to instantiate. And that logic can be encapsulated, can be built into, coded into what we commonly refer to as a factory. So this factory is responsible for keeping the business logic of creation of something of a particular shared type. In this scenario, I, in the general case, or when we're using a specific example, it would be animal. So we have a factory that's responsible for a particular creation mechanism, a particular way of constructing animals. So if you have two factories, then you have two ways of creating animals. They both create the same thing. But they create them in different ways. And here are two important points to remember. They create them in different ways, and, I should say, or they create different subtypes. So I think we need to get a little bit more concrete. So what I'm saying is that we have sort of two things. We have the things that we are creating, and we have the factories that create these things. So let's say that these are the things that we're creating, right? Let's use concrete names here. So let's say that this was dog, and this was cat, and this was duck. And this main class is animal. Sorry for being extremely sloppy. I think you can follow along. So you have that, right? These are the things that we're creating. You can think of this as the data, right? We want to create some kind of data. We want to build some kind of value object. It doesn't at all have to be a value object, but just for the sake of the example, it might be more simple to think about it that way. So these are the things we're creating. But then on the other hand, we have another thing, which is the way in which we can create these things. Let's remove this stuff. Let's say that what we can have is, for example, random creation. Actually, let's call it factory. So we have the random factory. So the random factory, to be explicit, we could even call it random animal factory. The random animal factory creates animals. Whether at any particular point in time you will get a dog, a cat, or a duck entirely depends on when we call the random factory, when we call create animal, which is a method that returns an animal. When we call create animal, we get back an animal. Whether that animal will happen to be a dog or a cat or a duck, we don't know. It entirely depends on what logic resides in this method. And the intent, in this example, the intent of the random factory, the random animal factory, is that this method will randomly create any of these. So let's think about the other creation factory that we talked about. So let's say that we also have something we call the balanced factory. So again, I should have called these like balanced animal factory and random animal factory. But because this one is called random factory, I'll call this one balanced factory. So the balanced factory has the same signature. In other words, it has a method that returns an animal and is called create animal. But this one, what this one does is that it randomizes one of these the first time you call it. So it has some kind of state. Right? So if you think about it, this factory does not have state because it's random every time. This factory actually has state. The balance between these different things matter. So either it uses state from the world or it uses state internally. So in other words, the first time it's creating randomly one of these. But if at any given time you have more of any one of these, then whenever you call create animal, then that thing will, that particular animal will be excluded from the randomness. I mean, again, remember that this is only part of the example. So in terms of the pattern, this doesn't matter. I'm just trying to find some kind of reasonable example of what could be different between these two different things. So in this particular case, we're making sure that upon every third creation, we'll have an equal number of the three different types of animals. Where in this one will converge towards the same number. So in this one, over time, we'll have roughly the same number of each of the different types, but at any point in time, it could be that it's skewed towards one or the others. Again, just an example. So I was trying to explain this without UML, but you can see that we're sort of slowly moving towards UML. So let's actually introduce some more UML-ness. So we're saying that we have these two things that are factories. And you probably already guessed that because I'm saying that this is a factory and this is a factory, then they should share some kind of ancestry. They should share some kind of a superclass or interface. So let's remove this divider and let's specify that interface. So in this particular scenario, I would probably call that an animal factory. And that thing, of course, has a method that returns an animal and is called create animal. And then, of course, these two classes are of that type. In other words, they implement the interface in case it's an interface, or they are of that type if it's an abstract class or if it's a class. In this particular scenario, it would probably suffice to have it as an interface. And honestly, this is really pretty much it. This is really pretty much the factory method pattern. Let's look at the definition from the Head First book. So, in Head First, they say that the factory method pattern defines an interface for creating an object, but lets subclasses decide which class to instantiate. Factory method lets a class defer instantiation to subclasses. Let's dig through this. The factory method pattern defines an interface. Remember that now when we're saying interface, we're not necessarily meaning interface as in class, interface, abstract class, this kind of thing, as in the keyword, but we're saying interface in terms of a contract. It defines a common contract under which you can refer to this particular thing. In other words, it could be an interface, but it could also be a superclass. So the factory method pattern defines an interface for creating an object. So the key point of factory method pattern, the key point of factory pattern is that in the end, you want an object. You don't necessarily know how you want to construct that object, why you want to construct that object, and what parameters you want to pass when constructing that object. Right? These are all unknowns, and that's why you want to defer. This is why you want to let somebody else take that decision. So, the factory method pattern defines an interface for creating an object, but lets subclasses decide which class to instantiate. And I would put more into this and just say that it's not only about which class to instantiate, it's also about what you actually want to pass to that that class that you're instantiating. Factory method lets a class defer instantiation to subclasses. Honestly, I'm not entirely sure what they mean here. I'm not sure if they mean that the common ancestor defers the decision to the subclasses, or whether they simply mean that whoever is using the factory defers to these factories. But since they're saying subclasses, they probably mean that the animal factory does not have to make the decision about which of the animal classes to instantiate and what to pass to it when instantiating, but rather these subclasses, the random factory or the balanced factory, these decide which object to construct and how. And that's it. So let's now clean up the mess we got on the whiteboard, and let's look at the generalized UML diagram from this book. So in this example, they use these terms. They have a product, which in our case was the animal. They have a creator, which in our case was the animal factory. The creator creates products. The animal factory creates animals. Then they have concrete product, which in our case were cats, dogs, and ducks. And concrete products are products, or implements products. And then the final piece is that they have concrete creator, which in our case was the random factory or the balanced factory, the random animal factory and the balanced animal factory. And these, of course, implements or are creators. In our case, the random animal factory was an animal factory, and all animal factories create animals, which in this case, on the general level, is a product. And the subclasses of these products are actually what is being created by any of these concrete creators. So you have a concrete creator that creates some kind of concrete product. But in order for us to be able to use polymorphism, we need to be able to treat all of the different concrete creators the same way, which is why we make all of the different concrete creators be creators. And since they all need to create things that might be different in type, they might be able to create dogs or cats or ducks or whatever, these things need to share some kind of common interface, some kind of common contract. And that's why the concrete products, we might have many of them, are products or implement the interface product. And just to go full circle with the methods here, the way they denote is that they mention that they have a factory method here, factory method, and of course then a factory method here as well. And of course, they're not explicitly denoting that in the head first book, but of course, the super important point is that these factory methods return something of type product. In other words, return something that is of type product, which in our previous example was animal. So just step back a moment and think about how we've divided different responsibilities between these different classes. In other words, what do these different classes do? What are these actually responsible for? So creators are, as the name implies, concerned with creation of some particular thing, of some shared type, which in this case is denoted as a product. So creators create products. But the creators might be abstract or it might be an interface because the key point is that we want to use polymorphism. Here's actually a very good place to talk about the simple factory non-pattern that they mention in the book. So the simple factory that they mention in the head first book is essentially this same UML diagram, but without the creator portion, without this upper portion. In other words, it's a way of having concrete factories, probably a single concrete factory that is responsible for the creation of products. So if you just think about that for a moment, that's actually a very intuitive idea. So it's like whenever we are in our application and we find some piece of logic that we repeat, and that logic is centered around the creation of objects of some shared type. So let's say we did that random thing. Right? We randomize a number and then we create one of three types. If we realize that we're duplicating that piece of code in many places, it's a very intuitive idea to say, actually, let's extract that into its own class and have a method for that. And let's just call that method whenever we want to use this piece, this randomizer logic and create one of these three objects. And that's fine and dandy, it's better than nothing, but it's not really using the power of polymorphism. It's not really, it's really a very, very small step. You could, just by introducing a tiny bit more abstraction, really gain much more flexibility. And that flexibility essentially stems from saying that actually this notion of being able to create something of this shared type is an idea of which I could have multiple instances. The idea of having some kind of strategy or some kind of way of constructing a product is something that could vary. And that varying we can very easily capture with the factory pattern, with a factory method pattern. So essentially we're then introducing this creator. We're just saying that when I extracted that logic and put that into a concrete factory, into a concrete creator, then I could very easily say that that is of a type so that I trivially could later create a different creator if I at a different point in time want to use some other kind of creator. creator. Going back to the discussion of responsibilities, so this side over here is responsible for creation, is responsible for how to create something. And this side over here is just actually the stuff that we want to create. So this is sort of the data that we want to produce. And again, it's not actually just data, so perhaps it makes more sense to think about it as a product, but it's this kind of stuff that we want to produce, and how we produce that is defined by the factories, is defined by the creators. So that's a lot of repetition, so I would guess that it's probably clicking now. If not, please do shoot something in the comment and let's discuss further. Before we wrap up, let me just try to give you a slightly different example that's very similar to this, but that might provide some context into when we would perhaps want to use this. And here it hopefully becomes more obvious why the factory method pattern is actually very powerful, and how it gives us a lot of flexibility that eliminates a lot of potential duplication and potentially saves us a lot of time. So let's say that we're building some kind of game, and let's say that this game has a number of levels, right? So you just think about some old arcade game that you've played, like the game where you're a ship that floats around in space, and sort of asteroids appear, like enter the screen. Then they slowly sort of travel around, and you're in this ship, and you can use your thrusters to move around in this space, and whenever you shoot one of these asteroids, they split into multiple asteroids, and you don't want to get hit by asteroids, but you get the point. You want to avoid anything, you want to split all of them and collect points and whatever. It's probably very easy for you to see how the factory method pattern would apply here. You have a factory that produces asteroids. The game sort of progresses, and as time progresses, asteroids are created. So you think about it this way. So think about that we have a game loop. I haven't been building a lot of games, but it's my understanding that this is the common way to do it. So there's some kind of iteration that goes on in the game all of the time. And at every tick, or at every step, at every lap of this game loop, we're calling a factory. We have some factory, and we're calling that factory, and we say create asteroid. Or just think about how we're sort of moving into something more general. We could even say create obstacle or something like that. So I'm just implying that you don't necessarily need to have a create asteroids and create power-ups and create la-di-da. You could even have them all in sort of the same method. But I mean, it depends entirely on your design and what you're actually trying to achieve. But let's say that we have create asteroid. Now that's trivial, and I think you can see how what we were doing before applies. You call create asteroid, maybe you're using some random. So you have something like the random asteroid factory, which maybe we even only have a single type, which is the asteroid. It doesn't matter. Maybe we just have that type. And the point is that you have some property in the asteroid, which is like the size of the asteroid. So sometimes you get a very large asteroid, and sometimes you get a very tiny asteroid, because you want to have some kind of dynamicness in the game, right? And maybe actually also you would potentially even randomize the position of the asteroids. You would have the x coordinate and the y coordinate in the asteroid. So of course we do that because you don't always want to have the same size asteroid that spawn in the same place all the time, etc. So we randomize the location, and we randomize the size of the asteroid. Right. Now, that's fine and dandy, but that's not very complex. Think about it this way. What if then you use a factory in level 1, and then you use another factory in level 2, then you use another factory in level 3, and so forth. But actually, when I say another, it doesn't necessarily mean that we would have the level 1 factory, and we would have the level 2 factory. Lots of different types. You can see how that would scale very painfully if you have like a lot of levels, or if you're actually creating a game that you want to be dynamic. Instead, you can think about it this way. What if we pass some parameters to the factory, and the factory uses those parameters to change some of the logic of asteroid creation? So maybe we pass two things. We pass the likelihood of the asteroid being big, and we pass so we didn't talk about that parameter before, but maybe we would have velocity. So, I mean, it needs to start in motion. So we would have a velocity x and a velocity y, for example. So maybe we pass another parameter, which is the speed. In other words, let's say that in higher levels, we pass a high speed value and a high likelihood of it being large. And in the lower levels, we pass a very low value for the speed and a very low likelihood of the asteroid being large. In other words, we've suddenly created a very nice set of classes that we can use to dynamically build very easy levels, build very easy conditions where we have small asteroids that don't move very fast. And at the hard levels, we are able to create large asteroids that move very quickly. This is just an example. I mean, of course, you could do this any way you want, but I think you're starting to see how, in a notion that's very similar to the discussion we had around strategy pattern, when you find good abstractions, when you find good factories and you parameterize them in good ways, you suddenly need fewer types. It's like you turn types into properties. And I think factory pattern is sort of a very helpful tool in trying to move away from a sort of class explosion into a world where we have a few key classes where there's a lot of variation that can happen by simply combining them in appropriate ways and instantiating them with different properties. So this is really the point about composition over inheritance. So I think you can see that if you keep on pushing on this sort of game example, on this sort of asteroid example, you can create a few key factories that you can use to create tons of different levels with tons of different behavior and actually very, very interesting behavior. And possibly we wouldn't even need to manually instantiate all of these different factories. We could simply, for example, compute the input numbers that we give to these factories based on the level number that we are on. If we're at level 4 is a multiplier that we use to compute the likelihood of the asteroid being large or the speed of the asteroid. And then we just instantiate that factory, and then we suddenly have a level 4, which we know is more difficult than level 3, but is less difficult than level 5. And I think then again, you can see easily how we could have the asteroid factory, and we could have the power-up factory, and the whatnot factory, and then we just keep on moving in that direction. So we're sort of parameterizing all of the portions of the system, which again moves the creation logic out of these particular levels. So it's not just that we don't need to have a class for level 3 and a class for level 4. It's even that, even if we have the same class for all of these, that class itself, the level class, doesn't at all need to be concerned about creation. It's just passed a few classes that are factories, a few classes that are responsible for creation, and then it just calls the appropriate method on these creation classes, which we previously called either create animal or create product. Alright, that's it. Thank you very much for watching. If you have any questions or comments, or feel that I've misrepresented or want to help other people in trying to understand what this pattern is actually about or when it's useful, please do shoot anything in the comments. And if you're new to design patterns, I highly recommend you to get this book. It's in the description. And of course, please remember to subscribe so that you won't miss the next pattern from this book. And finally, again, thank you for watching. I'll see you in the next one.